Something strange is happening with 3I Atlas right now. New images from NASA and the Mars orbiters show jets firing in directions that simply do not match normal comet physics. A sideways plume, a forward stream, and a brightness pattern that keeps shifting in real time. Scientists are racing to understand whether these behaviors are natural outgassing, unusual rotation, or signs of something entirely different happening around this interstellar visitor. And the newest data coming in today raises even more questions. NASA has coordinated a multi-platform campaign that includes the Hubble Space Telescope, the James Webb Space Telescope, solar observatories such as SOHO and Stereo, and several Mars orbiters that can view the comet from very different angles. A recent NASA update highlighted at least a dozen assets imaging the object since its discovery in early July 2025, turning 3I Atlas into one of the best observed interstellar visitors so far. The goal is to connect changes in brightness, jet structure, and tail morphology with three-dimensional geometry, instead of relying on a single line of sight from Earth. Mars-based instruments have played a central role. The Mars Reconnaissance Orbiter slewed its high-resolution camera away from the planet to capture side-on views of the comet and jets when 3I Atlas passed about tens of millions of kilometers from Mars in early October. At the same time, the MAVEN mission measured ultraviolet emissions from hydrogen around the comet and from the surrounding interplanetary medium. These data complement images from Earth-based telescopes that see the same structures projected on the skyplane. Radio facilities have now joined the campaign. The Meerkat Array in South Africa detected hydroxyl emission from the comet, a classical signature of water molecules being broken apart by sunlight. This confirms that at least part of the activity is driven by ordinary sublimation of ices, even though the detailed composition is unusually rich in carbon-bearing species. Taken together, the current dataset shows a clearly cometary object whose fine-scale behavior still challenges simple models. At the same time, the European Space Agency has used its ExoMars Trace Gas Orbiter to refine the orbit. By combining precise astrometric measurements from Mars with Earth-based tracking, ESA reports roughly an order of magnitude improvement in the predicted position of 3I Atlas over the coming years. That result is important for planetary defense and for planning follow-up observations, because it narrows the corridor where the comet will appear on the sky and confirms that its path remains entirely safe for Earth. The most discussed anomaly in the latest images is the geometry of one of the jets. High-contrast frames from Mars now show a narrow, collimated feature that appears to extend roughly sideways from the nucleus, close to perpendicular to the sun direction. This contrasts with the more familiar sunward and anti-sunward structures seen in previous Hubble and ground-based images, where the main jet seemed to point almost along the direction of motion, while the dust and gas tails were pushed away from the sun. In standard comet physics, the orientation of jets and tails is controlled by three solar-driven processes. Local solar heating on the nucleus creates gas jets that roughly point back toward the illuminated source region. Solar radiation pressure pushes dust away from the sun, so dust tails tend to point anti-solar. The solar wind guides ionized gas into an ion tail that also points away from the sun along the magnetic field. All of these effects have a preferred direction tied to the sun, even when rotation and viewing geometry add curvature. A sideways jet that remains straight on scales of thousands of kilometers is therefore unusual. If the apparent right angle is real and not a projection effect, it means the material in that jet is not being dominated by solar radiation pressure or the solar wind. Simple rotation of a sun-heated jet would normally produce a curved or spiral pattern, not a long straight feature that stays almost exactly perpendicular. That is why some analyses treat this as a genuine anomaly rather than just a striking image. Avi Loeb and collaborators have argued in public essays and interviews that such a geometry could, in principle, be consistent with active control on a technological object. For example, a directed outflow used for navigation or for clearing small particles. Other astronomers, including comet specialists, point out that the data are still noisy, that the images are affected by spacecraft motion, and that unusual activity on a rotating, irregular nucleus can create complex structures without invoking new physics. Independent teams have already begun modeling whether a fragmented nucleus, multiple vents, or transient outbursts could reproduce the observed pattern purely through natural processes. From a scientific perspective, the key question is not whether 3I Atlas is artificial, but whether the jet morphology can be reconciled with known physics of icy bodies moving through the inner solar system. To answer that, teams are analyzing time sequences of images from different spacecraft, reconstructing the three-dimensional geometry, and comparing it with simulations of rotating comet nuclei. The sideways jet remains a focus of that work, but it is being treated as a test case for cometary modeling, rather than a confirmed sign of exotic technology. Spectroscopic measurements from James Webb and other observatories show that the coma of 3I Atlas is chemically unusual compared with typical solar system comets. The ratio of carbon dioxide to water appears to be several times higher than values commonly measured in comets from the Oort cloud or Kuiper belt. Carbon monoxide is also elevated, and the optical colors of the dust make the nucleus and inner coma among the reddest small bodies yet observed. These properties match what laboratory experiments predict when simple ices are irradiated by galactic cosmic rays for billions of years. In such experiments, sustained exposure to high-energy particles gradually converts carbon monoxide into carbon dioxide and synthesizes complex organic residues. The surface becomes coated in a dark, reddish, carbon-rich crust that can reach thicknesses of many meters. When sunlight finally warms such a surface, during a close stellar passage, the uppermost layers dominate the outgassing and dust release, masking whatever composition exists deeper inside. Analyses of the erosion rate of 3I Atlas as it passed through the inner solar system suggest that only about the upper meter of material has been significantly removed so far. That means current measurements mostly probe this cosmic ray-processed crust rather than pristine interior ice from the object's birth environment. In other words, the comet is telling scientists more about long-term chemical processing in the interstellar medium than about the exact composition of the original protoplanetary disk that launched it. This has led to a proposed galactic cosmic ray processing hypothesis for interstellar comets. In this picture, most interstellar icy bodies accumulate a thick, chemically modified shell during their journey between stars. When they finally pass near a new host star, the first activity we observe is dominated by this processed layer, making them look compositionally extreme compared with local comets. Only if an object fragments or experiences very deep erosion would astronomers gain a clear view of more primitive interior material. For 3I Atlas, current chemical data therefore sit in an interesting middle ground. On one hand, they reinforce the classification as a natural icy body, since the trends in carbon-bearing species and color can be explained by known radiation chemistry. On the other hand, they warn that even with powerful telescopes, interstellar visitors may rarely offer a simple window into their home systems. Instead, they serve as integrated records of galactic processing that must be carefully untangled from any signatures of origin. Alongside jet morphology and composition, the trajectory of 3I Atlas has been a central topic. Precise orbit solutions now combine optical astrometry from many observatories with tracking data from spacecraft near Mars. The European Space Agency reports that ExoMars trace gas orbiter measurements have improved the predicted position of the comet by about a factor of 10 compared with early post-discovery solutions. That refinement reduces the uncertainty region on the sky and confirms that the object poses no impact risk. Early analyses indicated a small, non-gravitational acceleration, similar to what is often seen in active comets, whose outgassing slightly perturbs their paths. Recent discussions, including public question and answer sessions with Avi Loeb, note that newer orbit fits keep this extra acceleration at a low level that is not statistically compelling. In practical terms, the trajectory remains dominated by gravity from the Sun and planets. There is no evidence that 3I Atlas is maneuvering toward any particular world. From the planetary defense perspective, the campaign has been an important demonstration. By rapidly repurposing spacecraft that were designed for other missions, such as Mars orbiters, space agencies have shown that they can quickly build a multi-vantage geometry for tracking an unusual object. Combining those measurements with ground-based surveys and networks, such as the Asteroid Terrestrial Impact Last Alert System, allowed teams to follow an interstellar body through the inner solar system with far better precision than was achieved for previous visitors. The same techniques will apply to future interstellar objects and to potentially hazardous asteroids. If a genuinely dangerous object were discovered on a short warning trajectory, being able to use existing spacecraft to cross-check its orbit from another part of the solar system would add valuable redundancy. 3i Atlas has therefore acted as a real-world test of distributed tracking and has helped refine software pipelines that merge data from many instruments. For comet science, the accurate trajectory also matters for interpreting non-gravitational effects. Once the purely gravitational path is pinned down, any residual deviations can be linked more confidently to asymmetric outgassing, fragmentation events, or other physical processes. With 3i Atlas, current solutions leave only small room for such effects, suggesting that while its activity has unusual features, it remains dynamically well-behaved on the scale of its passage through the inner solar system. A recent round of media coverage has focused on the idea that 3i Atlas might be actively clearing micrometeoroids from its path. The argument, based on interpretations of forward-pointing and sideways jets, suggests that a directed beam of material or light could, in principle, sweep away small particles before they collide with the main body. In that scenario, the visible plumes would be signatures of navigation or protection, rather than of passive outgassing. From a physical standpoint, such a concept would require sustained, precisely collimated emissions over enormous distances. The sideways jet alone appears to extend for many thousands of kilometers in current images, and any hypothetical meteor clearing system would need to remain aligned with the direction of motion, while the object rotates and travels through a complex environment of dust and plasma. Known natural processes on comets do not provide such control, but the reverse is also true. There is no direct measurement showing that particles are being systematically swept aside. Current datasets show clear evidence for water breakdown products, carbon-bearing gas, and dust shaped by solar radiation and the solar wind. They do not yet provide time-resolved maps of particle densities along the path of 3i Atlas, or measurements of how any potential debris field responds to its passage. Without that information, claims of intentional clearing remain speculative. Mainstream analyses therefore treat the meteor clearing idea as an interesting thought experiment, rather than an established description of the object. In parallel, several independent groups have published or are preparing studies that re-examine the claimed anomalies. Some focus on whether image artifacts, satellite trails, or processing choices could exaggerate apparent jet angles. Others explore whether a fragmented, precessing nucleus with multiple vents could naturally create both a forward-pointing jet and a transient sideways structure, especially when viewed from changing geometries near Mars and Earth. These studies aim to test natural explanations rigorously before invoking new categories of objects. Looking ahead, the most useful discriminant will be better data. Additional imaging from Hubble, James Webb, and large ground-based observatories, along with continued monitoring by spacecraft, will build longer time series of jet evolution and brightness changes. The Vera Rubin Observatory, now beginning its survey operations, is expected to find many more interstellar comets in the coming years. When those future objects are studied with the same intensity, astronomers will be able to see whether the kinds of behavior seen in 3i Atlas are rare outliers or part of a broader population. More data on 3i Atlas is incoming, and some of it is expected to change our understanding of its behavior. Subscribe to stay ahead of each confirmed update as it arrives. Like the video and share it so others can follow the developing picture. And thank you for watching.